I've been asked to give an introductory talk. I'm not an expert on early mathematics, but the idea is that I'm going to sort of set the scene by talking a bit about Egypt and Mesopotamia and about China and India. And then it's up to the other speakers to develop what I say or correct it as necessary. So I'm going to start, so the cultures we're going to be looking at are some of the ones on the timeline here. So I'm going to start the story with Egypt and Mesopotamia, which are shown on this map here. Ancient Egypt developed along the valley of the Nile, while Mesopotamia, as its name suggests, middle of the rivers, it developed between two rivers, the Tigris and the Euphrates. But as we'll see, the surviving primary sources of the two cultures are very, very different. We know relatively little about the Egyptian world because their writings were on papyrus, which rarely survives the ravages of the centuries, and only a handful of mathematical papyruses still exist. On the other hand, Mesopotamian mathematics was imprinted on clay tablets that were baked in the sun, and many, many thousands of these have survived. And incidentally, what I call Mesopotamian mathematics is often called Babylonian mathematics, but that term is increasingly going out of use because no mathematical tablets from Babylon have actually come down to us. So let's move to Egypt first, and when studying the mathematics of ancient Egypt, we're immediately struck with how little the subject changed over a period of some 3,000 years. Egyptian society was centered around the River Nile, which irrigated the land so that crops could grow and cities could develop. The civilization was a hierarchical one, headed by the mighty kings and pharaohs. And from about 2700 BC onwards, the pharaohs desired to be buried in massive pyramids. And the oldest of these, King Djoser's step pyramid at Saqqara, was constructed in horizontal layers and supposedly designed by Imhotep, the celebrated Grand Vizier and architect. But much better known are the magnificent pyramids of Giza, which date from about 2600 BC and attest to the Egyptians' extremely accurate measuring skills. In particular, the Great Pyramid of Cheops has a square base whose sides, of length 230 meters, agree to less than 0.01%. Constructed from over 2 million blocks, and averaging about 2 tons in weight, and transported 50 miles by a whole army of workers, the pyramid is an impressive 146 meters high. And even more remarkable, it's not solid, it's got an intricate arrangement of carefully planned internal chambers and passageways. Well, as I said, our knowledge of later Egyptian mathematics is scanty, deriving mainly from a small number of fragile primary sources, notably the Moscow papyrus, which is about 1850 BC, and the Rhind papyrus, which you can see a bit here, from about 1650 BC. And this is in the British Museum, though I believe they're still hiding it away, and I think we ought to put pressure on them to exhibit it again. So, as I said, here's part of the Rhind papyrus. It shows some geometrical problems, with one of them that I've blown up here so that you can see some of the details. And as you'll see, although some of the problems superficially seem practical in nature, their main purpose seems to have been educational, in fact, for the training of scribes. And here you can see an Egyptian scribe enjoying his mathematics. So how did the Egyptians count? Well, like most counting systems, theirs was based on 10, but it used different symbols for 1, 10, 100, 1,000, and so on. It had a vertical rod for 1, a heel bone for 10, a coiled rope for 100, a lotus flower for 1,000, and so on. And you recall, of course, that Roman numerals similarly use different symbols for 1, 10, 100, and 1,000. And then a number is represented by, with the appropriate number of each symbol, written from right to left. So here are 367, 367, and 756, 756. And then you add them together by collecting the symbols together, and whenever you've got a group of 10, you just replace them by the next symbol. So 10 rods gives a heel bone, and 10 coiled ropes gives a lotus flower. Multiplication is more interesting and was done mainly by using successive doubling and halving. The multiplication by 10 was also simple, because you just replace each symbol by the next one. So here is a calculation of 80 times 14, taken from the Rhine Papyrus, problem 67. So you write 80, which is 8 of these, and then you replace each heel bone by a coiled rope to give you 800. You then return to your 80 and double it to get 160. As I say, they knew how to double, and then you double it again to give 320. And now if you add, now you're multiplying 80 by 14, so if you add the rows corresponding to 10 and 4, then you get the answer. It's this plus this, which is just this, which is 1120. Here's a more complicated problem, which we might think of as algebra. It's number 25 on the Rhine Papyrus. A quantity and its half added together becomes 16. What is the quantity? So in modern algebraic terminology, which of course they didn't use, we'd be trying to solve the equation x plus a half x equals 16. And the method that they used, or they frequently used, was called the method of false position. Basically, you guess an answer. You guess a convenient answer. It's bound to be wrong, but then you sort of scale it up or down as necessary. So because you've got a quantity in its half, it's convenient to start with 2. So a quantity in its half is 3. But you don't want 3, you want 16. So you've got to scale the 3 up to 16, and then the same scaling applied to 2 will then give you the answer. As I say, as many times as 3 must be multiplied to give 16, so many times 2 must be multiplied to give the required number. So doubling is used. You start off with the 1 and the 3, and you keep on doubling. And then to get the 16 here, the corresponding things here are 5 and a third. So doubling is used, as is multiplication by 2/3. They use fractions of the form 1 over something, but they also use 2/3. And the appropriate rows are then singled out and added, and you get the answer 10 and 2/3. And finally, under the heading "Do it thus," they say the answer is 10 and 2/3, and they check the answer. Okay? So this mention of 2/3 and 1/3 and so on leads us to Egyptian fractions, which are very different from the ones that we use. So apart from 2/3, all their fractions were what we call unit fractions or reciprocals, 1 over something. So for example, where we would write 2 over 11, they wrote 1 over 6 and 1 over 66. No one's really quite sure exactly what method they used to get these unit fractions. There has been a lot of discussion about these, but if you add these two together, you get what we would call 2 over 11. And here's another example. 2 over 13 is 1 over 8, 1 over 52, 1 over 104, as you can quickly calculate in your head. And their ability to calculate with these unit fractions can be seen from problem 31 of the unit papyrus, of the Rhine Papyrus. A quantity, it's 2/3, it's a half, and it's 1/7 added together give you 33. What is the quantity? So if we were doing it using modern algebraic notation, we'd say x plus 2/3 x plus a half x plus 1/7 x is 33, and we would solve it to give 14 and 28 97ths. But if you look in the Rhine Papyrus, this is their answer. And it shows an absolutely remarkable ability to calculate with these unit fractions. Okay, have you checked that? Right. Well, how did they do this? They actually used extensive tables of numbers, breaking the fraction down to a succession of fractions of the form. To do a calculation, they had tables of numbers. They broke the fraction down to a succession of numbers of the form 2 over n, and they had this table giving 2 over n for n is equal to 5, 7, 9, all the way up to 101. And you can see that here. A rather different type of problem they looked at involves the area of a circle. Problem 48 asks the scribe to compare the areas of a circle and its circumscribing square. So that's the portion of the papyrus, and here is the problem. And to compare the square and the circle, first of all, you start with the square, and they chose a particular length of side. They chose 9, and then, so you want 9 times 9, so you keep on doubling. You've got, here's a 9, and here's a 72, and then you add the 1 and the 8, and that'll give you 81 as the area of the square. And for the circle, they did a similar thing, but instead of starting with 9, they started with 8. And they ended up with 8 times 8 is 64. So why did they look at 8? Well, basically, the method they use, as far as we can judge, is that they took the diameter. They found in practice that if you take the diameter and remove 1/9 of it, so you've got sort of 8/9 of it, and you square that, that gives you a good approximation to the area. It has been suggested that it's something to do with an octagon, but I think that's been discounted now. So basically, if you take 8/9 squared and then put it in terms of the radius, it gives you an area of this, which corresponds to the value of pi of about 3.16, which is really quite remarkable for the time. So that's all I'd like to say about Egyptian mathematics, and I'd now like to go on to Mesopotamian. And although it dates from, or the tablets I shall talk about date from the same time as the Rhine papyrus, the tablets we'll look at are very different in content. So using a wedge-shaped stylus, they imprinted symbols in moist clay, and this is called cuneiform writing, and the tablet was then left to dry in the sun, which is why we've got so many. Actually, I think we've got hundreds of thousands of clay tablets that have survived, and many thousands of these are mathematical. And there's been a lot of exciting work done on them recently by people like Eleanor Robson and others. Well, unlike the Egyptian counting system, which is a decimal system with different symbols representing the powers of 10, the Mesopotamian system was a place value sexagesimal system. That is, it's a system based on the number 60. And it used only 2 symbols. It used this for 1 and this for 10. And then a symbol like this, there are 41, there are 41 60s added together with a 40. Okay, 41 and 40 60s. But the problem is you have to look at these things from the context, because this can be broken up in different ways, and there aren't. It might be a 60th of this, or it might be 60 times this, or whatever. So the same succession of symbols might refer to, say, for example, 60 plus 2, or 60 squared plus 2 times 60, or 1 plus 2 60ths, depending on the context. But this idea of context is something that may seem strange to us, but in fact it's something we use all the time. 650, that might represent to us time, 10 to 7. Or it might be the cost of a bus trip to Cambridge, £6.50. Or the cost of a flight to Singapore, £650. If we say 650 from the context, we usually know what we're talking about. Well, there are essentially 2 types of mathematical tablet. There are the table texts listing tables of numbers that are used in calculations, and problem text in which problems are posed and solved. And recently Eleanor Robson has suggested a 3rd type, because of course these clay tablets were used for educational teaching purposes, and there are quite a lot of tablets which could be described as rough work. We've got a student who's sort of doing little problems on their clay tablet, just as we would on a scrap bit of paper. There are several table texts, and some of these present multiplication tables. So here's the 9 times table. This is a drawing of it, and here's actually a picture of the 5 times table. So you can actually see down here the numbers 1, 2, 3, up to 14, and multiply them by 9, and you get the answers on the right. So they have these tablets that they can refer to when they're doing their calculations. And there are lots of other tables. There were tables of reciprocals and so on. Quite a lot of things that they could use, just the way that we may use tables. As far as problem text is concerned, here's an example of a problem from problem text. It's this one. I found a stone but did not weigh it. After I weighed out 6 times its weight, added 2 gin, that's, don't misinterpret that, and added 1/3 and 1/7 multiplied by 24th, I weighed it 1 mana. What was the original weight of the stone? The problem is clearly not a practical one, because if you want the weight of a stone, why not just weigh it? But in fact, it's one of 22 problems of a very similar type, all on the same tablet, and all ending up with 1 mana. So this leads us to believe that the tablet was a teaching tablet. Now, one can find from the context, analysing these things, you can find that 1 mana is 60 jin, and so let's do the calculation. So if x, and again, this is modern notation which they wouldn't have used, so if x is the weight of the stone, you take 6 times its weight and add 2 jin, so that's 6x plus 2. Then you add 1/3 of 1/7 multiplied by 24. So here's 1/3 of 1/7 multiplied by 24. Of what? Not the weight of the stone, but of the stage you've reached in the calculation so far. And it's by looking at these things and working out what's going on, we actually realize that what you put here is a 6x plus 2, and that's equal to 60. So x is 4 1/3 jin. And then they give a check, which you can do, and you find that you get the right answer. Our next problem is rather more complicated. I have subtracted the side of my square from the area, 1430. That means 14 60s plus 30. And here's the solution. You break off half of 1, that's 0.30. 0.30 you multiply, you add 0.15 to 1430, result 1430, 15. This is the square of 2930. You add 0.30, which is what you multiplied by, to 2930, and you've got the answer 30, the side of the square. So what's going on here? Well, in modern notation, you're subtracting the side of a square from an area. Well, of course, that's something you can't do geometrically. But if you think of the side as x in modern terminology, and the area is x squared, so you've got x squared minus x is this number here, which is 870. So in modern terminology and modern ways of thinking about it, it's solving what we now call a quadratic equation. And the method is, so you write down 1, which is the coefficient here, and you halve it, and you square, and which is that, and then you add it to the 870, okay, and then you take the square root, and then you add that half, which gives you 30, and the answer is 30. 30 squared minus 30 is 870. So they had a method for taking a particular, what we would now call a quadratic equation, and finding a solution of it. And in fact, if you apply the similar thing to x squared minus bx equals c, the same sort of method, they didn't give a general method, but they gave several examples. They were solving particular equations, and if you do it, you actually get this, which is very much like, it's essentially the quadratic equation formula that we have now. But of course, that's looking at it from modern terms rather than from the times of the time. There's a particularly unusual tablet I want to show you before I move on. And this shows a square with its 2 diagonals. And then there are various numbers imprinted in the clay. The numbers 30, 1, 24, 51, 10, and 42, 25, 35. And what it turns out is that these refer to the side of the square. That's 30, the square root of 2, and the length of the diagonal, which is 30 times the square root of 2. So here's 30, and here's the square root of 2, and here's the length of the diagonal. And the amazing accuracy of the square root of 2, they give us 1, 24, 51, 10. And if you want to see how accurate it is, if you square it, you get 1, 59, 59, 59, 38, 1, 40, which differs from 2 by a really tiny amount. So it's amazing how accurate they had got the square root of 2 at the time. Well, there are other well-known tablets. There's one called Plimpton 322, which is very controversial, but that would take me quite a lot of time to talk about, so I'm going to leave that one. I did talk about it some years ago in one of the Gresham lectures, so it's all on the web if you want to look. And there's been a lot of discussion, a lot of controversy about it, what it really means. Some people say it's right-angled triangles and solutions a squared plus b squared equals c squared. That's largely been discounted by Eleanor Robson and others, and she has written some very attractive articles about what she feels it's really all about. But rather than getting involved, the text is called Plimpton 322, and her name is Eleanor Robson. I'm sure if you Google her, she wrote a very attractive and easy-to-read article in the American Mathematical Monthly, I think in 2002 perhaps, January 2002, and it's well worth looking at. But it's very controversial, so I won't get involved with that. And I'm now going to turn to the mathematics of China and India. Around 250 BC in India, King Ashoka's edicts were written on vertical pillars around the kingdom, and numerical information appeared on these pillars. It was written in a place system based on 10, and seems to be in the origin of what we now call the Hindu-Arabic numerals, the numerals we use now with its separate columns for units, tens, hundreds, and so on. So instead of having different symbols for 1, 10, 100, 1,000, and so on, you've just got the symbols 1 to 9, and later 0 to 9, and then all the other numbers you write in terms of those, and of course it's the position of the number that counts. So the two threes in 33 play different roles. Okay, one is 3 units and the other is 3 tens. Well, the Chinese had a couple of different counting systems, but they had counting boards in which there were separate compartments for units, tens, hundreds, and so on. So here you can see 6,736, and here's 2,101 as we would now write them. So there are only 9 different symbols, from 1 to 9, although each of them had 2 forms. Here's the vertical form, and then the other form, you turn them on their sides, and you get these different forms here. And I think it seems to be the reason for that is so that you can actually distinguish them more easily if they're in consecutive boxes. Okay, so for example, the 6 here is the upside-down version of the 6 here, but here the 2 ones are the same. And if you have a 0, then you just leave the box empty, the compartment empty. I mean, in this context, it might have been natural to introduce a 0 symbol for the empty box, but they didn't actually do so. But the Indians did, however. Whether they were familiar with Chinese counting boards is unknown, although the Chinese certainly visited India, and the boards were transportable, a bit like laptops, well, not quite like laptops. So it's quite possible. But in any case, the Indian number system, it did develop as a place value system based on 10, using only the numbers 1 to 9, unlike the Egyptian and Greek symbols, but eventually, and possibly around 400 AD, bringing in the number 0. So I'd like to look at the mathematical activities of China and India in more detail, although primary source material is very sketchy, and in particular the Chinese wrote on bamboo and on paper, and not very many of these things have survived. First of all, there's an ancient Chinese legend about the Emperor Yu standing on the banks of the River Lo. This was a tributary of the Yellow River, when apparently a tortoise or turtle emerged from the river with a magic square on its back. This may not be a very common thing. It certainly was a pattern of numbers, and it looked a bit like this. Okay. It's a 3 by 3 magic square in which the sum of the numbers in each row and each column and the two main diagonals were all the same. 6 plus 9 plus 2 is 15, 4 plus 5 plus 6 is 15, and so on. Over the centuries, this particular pattern of numbers came to acquire great religious and mystic significance and appeared in many different forms, as you can see. And although Emperor Yu lived about 200 BC, there is no evidence of the story until much later, and possibly as late as the Han dynasty, which started in 206 BC. There's a very, very nice book by Frank Swett all about the origins of the Lo Shu, and it's not really known when the story dated from. Current guesses seem to be about 1000, 1200 BC, but no one is really quite sure. Anyway, coming back to 206 BC, it was around that time that some classic Chinese texts appear, and one of these was, had the snappy title of The Arithmetical Classic of the Gnomon and Circular Paths of Heaven, which contained a celebrated dissection proof of Pythagoras' theorem. I'm sure you've seen various dissection proofs of Pythagoras' theorem. Here is one, and using a picture like this, one can obtain the famous Pythagorean theorem. One should probably say Pythagorean theorem because there's no evidence that Pythagoras really had anything to do with the theorem. Another classic Chinese problem of the time, or problem type of the time, which can be solved using the Pythagorean theorem, are the problems of broken bamboos. So here's an example of this. So there's a bamboo 10 feet high, and the upper end, well, it's not feet, I think they used chi was the unit, but we'll call them feet anyway. You've got 10 feet high, and the upper end of it is broken, and it reaches the ground at a distance 3 from the stem. Find the height of the break. And so in modern algebraic notation, if we were solving it now, and of course the Chinese didn't have this, if you call this answer x, and this is y, which is the same as 10 minus x, and then you use the Pythagorean theorem, then you can calculate the answer. Okay, so you've got these equations here. And it's quite a complicated, quite a complicated answer. So they seem to be able to solve problems of this kind. And this particular bamboo problem appeared in another great early text, the 9 chapters on the mathematical art. This is probably the most important of the Chinese texts. It's a remarkable work which contains 246 questions with answers, but with no working shown. And it may have been used as a textbook, with the methods, of course, given orally. It deals with both practical and theoretical matters. For example, there are problems from agriculture, business, surveying and engineering. There are discussions of the areas and volumes of various geometrical shapes, the calculation of square roots, even the calculation of cube roots, study of right-angled triangles, and the solution of simultaneous equations. And the last area in particular is very remarkable. Here is an example. There are 3 types of grain, which we'll call good, moderate, and poor. 3 bundles of good grain, 2 bundles of moderate grain, and 1 bundle of poor grain take up 39 measures. 2 bundles of good grain, 3 bundles of moderate grain, and 1 bundle of poor grain take up 34 measures. 1 bundle of good grain, 2 bundles of moderate grain, and 3 bundles of poor grain take up 26 measures. How many of each type are there? So these days we would write down 3 simultaneous equations, and that's what's done here. Except that here they've written them in a table from left to right and vertically. Okay. And we then manipulate these equations using what is now called Gaussian elimination. And that's exactly what the Chinese did here. The method of Gaussian elimination, which dates from about 1800, is exactly the same as the method that the Chinese used 2,000 years earlier. And so they go through the same sort of, I mean, it's all rotated through 90 degrees and so on, but it's essentially exactly the same method, and you end up with the answers 2 3/4, 4 1/4, and 9 1/4. So it's exactly the same as the one that Gauss gave later, but Gauss is the one that seems to get the credit now. Another preoccupation of the Chinese was the evaluation of pi, the ratio of the circumference of the circle to its diameter. And we've already seen how the Egyptians tackled it. The Mesopotamians also had a method which gave a slight underestimate for pi, about 3.125, I think theirs was. Archimedes got estimates for pi by comparing the perimeters of polygons drawn inside and outside the circle. So he started off with a circle, he drew a hexagon inside, a hexagon outside, calculated the perimeters, and he got estimates, upper and lower estimates, which weren't very good. So he then doubled the number of sides to 12, 24, 48, and then 96, giving the lower estimate of 3 and 10 71st, and the upper estimate of 3 and a 7, 22 over 7, the one that we all know. Well, in his classic In the Island of the Sun, of around 260 AD, Liu Hui carried on this process, continuing doubling the polygons. I mean, they obviously didn't draw these polygons, but they had a method of doing the calculations whenever you double the number of sides. And he was concerned with areas rather than perimeters, but it's still the same idea. And he doubled up from 96 to 192. He eventually got to 3,072 and got the estimate, which in our decimal notation we would write as 3.14159. But even more impressive, around 500 AD, Zhu Zhongji and his son extended this to polygons with 24,576 sides, and thereby obtained pi to what we would now think of as 6 decimal places, 3.141592, and it's between 6 and 7. And they also replaced the crude estimate 22 over 7 by the better one, 355 over 113, which gives pi to 6 decimal places, and that approximation wasn't rediscovered in Europe until 1,000 years later. And further improvement didn't come until around 1400 in the Islamic world. Well, I'd like now to look at Indian mathematics, concentrating in particular on 3 mathematicians, Aryabhata the Elder, Brahmagupta, and Bhaskara. Aryabhata looked at Diophantine equations. A Diophantine equation is one where we're interested in finding whole number solutions to equations. And Aryabhata gave the first systematic treatment of these around 500 AD. He was also interested in trigonometry, which had come in about 500 years earlier with Hipparchus, and constructed tables of the sine function. Brahmagupta, possibly the greatest of the 3, discussed the idea of 0 as a number to calculate with, showed how to solve quadratic equations, essentially the Mesopotamian way, and looked at a particular type of equation that we now call Pell's equation. Bhaskara, much later, wrote a famous arithmetic book called Lilavati, in which he showed how to simplify certain numbers using square roots. He had essentially formulae like this. So in particular, he had a formula that can be used to show the square root of 17 plus the square root of 240 is equal to root 12 plus root 5. So let's look at these. Aryabhata, one of his main contributions was to sum various arithmetic series. For example, if we look at an arithmetic progression, such as 5 plus 7 plus 9 plus ... plus 31, or this one here, then you can find the sum of all the numbers in it. According to Aryabhata, the desired number of terms minus 1 halved multiplied by the common difference between the terms plus the first term is the middle term. This multiplied by the number of terms desired is the sum of the desired number of terms. Well, that's not exactly user-friendly from our point of view, but it was a description in words. Of course, the algebraic notation that we use today wasn't available. But another version that he gave is you take the sum of the first and last terms and you multiply it by half the number of terms. So this gives you the expressions that we use now. In the 7th century, Brahmagupta gave rules for calculating with 0 or cipher, and also positive or negative numbers. we're not quite sure when 0 first came in. It might have been 400 AD. The first actual written record, I think, is not till about 800. But there is this description of how to use 0. So 0 is not just a placeholder, it is a number to calculate with. And so in the 7th century, Brahmagupta said, the sum of cipher and negative is negative. If you take 0 and add a negative number, you get a negative number. Of positive and naught, positive. Of two ciphers, cipher. I'm not quite sure why he uses cipher and naught. Are they interchangeable? If we have an expert here, that would be good to know that. He also said that negative taken from cipher becomes positive, and positive from cipher is negative. Cipher taken from cipher is naught. The product of cipher and positive or cipher for a negative is naught. Of two ciphers, it is cipher. And then he gets very confused. Cipher divided by cipher is naught. Positive or negative divided by cipher is a fraction with that as denominator. Cipher divided by positive or negative is, well, and so on. It would be many centuries before mathematicians really understood the problems caused by dividing by 0. And both Brahmagupta and Bhaskara worked extensively on a particular equation now known as Pell's equation, which is an incorrect assignation by Euler. So this equation has the form cx squared plus 1 equals y squared, and we're required to find whole number solutions x and y for given values of c. So here's one example. Tell me, O mathematician, what is that square which multiplied by 8 becomes together with unity a square? So you're trying to find integer solutions of 8x squared plus 1 equals y squared. And they gave methods for taking a solution and getting new solutions. In fact, as many new solutions as you like. Because you can spot quite easily that if x is equal to 1, this is 9, so y is equal to 3. So what you do is you write 1, 3, 1, 3. And then you multiply. You go 1 down to this 3. 1, 3 is a 3. 1, 3 is 3. If you add these two, you get 6. And that's a new value that works for x. And that if you put 6 in here, you get y is equal to 17. And of course, they didn't use this algebraic notation, but this is essentially the method that they use. To get another solution, you write 1, 3, which is what you had before. You have the new one, 6, 17. 1, 17, 17. 6 3s are 18. 18 and 17 give you 35. That's another x that works. And you can work out that y is equal to 99. And so you can generate as many of these as you wish. And they were able to do some really quite remarkable calculations. The most difficult ones were C is 61 and 69. 61 has very, very large solutions. 67 has easier ones, but they were able to get answers like the smallest solution is 59, 67, and 48,842. And that's small compared with the one for 61. But the margin was too small to write that one out. Before I finish, I'd just like to talk about one more topic, and this was early work on permutations and combinations, the area of maths that we now call combinatorics. In the 6th century BC medical treatise, Sushruta was investigating a number of ways of systematically combining 6 tastes used in cooking. So you have sweet, acid, saline, pungent, bitter, and astringent. And he found that you can choose 2 of them in 15 ways, 3 of them in 20 ways, and so on. Around 300 BC, the Jainas similarly studied combinations of 5 senses, and also, for some reason, combinations of men, women, and eunuchs. This gave rise to the phrase having a eunuch solution, of course. And around 200 BC, Pingala investigated combinations of short and long syllables in a metrical poem, da, didi, dadi, and how many different ways are there of arranging these. Much more substantial was the work of Varahamihira around 550 AD, who desired to find the number of perfumes that could be made from 4 ingredients chosen out of 16. So he must have had some sort of method for calculating this. These you can list. These are much more difficult. And he gave the correct answer of 1820. And Bhaskara gave general rules for what we now call n factorial, n choose k, and so on. So although Indian mathematicians were skilled in dealing with permutations and combinations, and binomial expressions were beginning to be studied, they never constructed what we now call Pascal's triangle, which lists these combination numbers. We call them binomial coefficients. They arise in multiplying out binomial expressions and also as combinations. And I thought I'd end up by just showing you a couple of Pascal's triangles. The earliest one we know is actually an Arabic one by Al-Karaji around 1000 AD. I think 1007 is the year that this came, so this is the earliest known Pascal triangle as far as I know, unless one of our experts tells an earlier one. But I'd like to end up with a Chinese Pascal triangle. This is from 1303, their treatise, The Precious Mirror of the Four Elements. So I thought it was a nice picture to end on. So thank you very much.